Welcome to the deep dive. We unpack complex topics, try to turn dense info into surprising insights, and today we're digging into something that's really captured everyone's imagination: AI systems like ChatGPT. How do they actually work? You've shared some, well, fascinating sources, foundational machine learning stuff, interviews with the AI architects themselves. Our mission, really, is to demystify these language models, how they handle words, predict text, generate answers, without all the hype and maybe the really dense jargon.
Exactly. And what's really remarkable is that while the public sees maybe mystery or these wild predictions, the core ideas, they're built on decades of research. We can trace those ideas, connect the dots for you, show that fundamentally these are incredibly sophisticated statistical engines.
Okay, so let's unpack that. Before an AI can even start to, quote, understand language, it needs to translate our words into something computable, right?
Yeah.
How does a machine even begin with something abstract, like a word, like red or, I don't know, book?
Well, yeah, connecting it to the bigger picture. All machine learning kicks off with data. For language, that means turning words into numbers, feature vectors. Technically, think of it like a list of numbers representing features of that word. A supervised learning algorithm, for instance, takes an input, maybe an email, converts the text into these vectors, and then uses that to decide, is it spam or not spam. Machines really dealing with numbers, not concepts like we do.
Right, numbers. So if you have categories, like you said, red, yellow, green,
hmm
how does it assign numbers? Is there a standard way?
Yeah, one basic way is something called one-hot encoding. It's pretty fundamental for turning categories into numbers the machine can use. So red might become, say, 100, yellow gets 010, green 001. Each one gets its own unique numerical code, simple binary format.
Okay, that makes sense for distinct things. But then you mentioned word embeddings like word2vec. That sounds like a bigger leap. What's different there?
It is a huge leap. The really profound idea with embeddings is, instead of just a unique number, each word gets this multi-dimensional vector. Think coordinates. Coordinates in this huge semantic space. And the distance, the geometric distance between two word vectors in the space, that actually represents how similar they are in meaning.
Wow.
So words that are conceptually close, numerically close, is not just numbers anymore. It's numbers that capture meaning, or at least relationships between meanings.
Yeah, that's powerful. Mapping meaning numerically. So how does that actually work for similar words like, say, book, article, paper? Why do they cluster? And how does it let you do those weird analogy things like man is to woman is king is to?
Queen, yeah.
Yeah.
It learns these relationships which are looking at context, massive, massive amounts of text data. Like the system sees, I almost finished reading the blank on machine learning millions of times. It learns that book, article, paper often fill that blank. They appear in other linguistic
Oh,
environments.
okay, because they share context.
Exactly. And the king is to queen thing, it works because the mathematical relationship, the vector difference between man and woman is incredibly similar to the vector difference between king and queen. You can literally do arithmetic, add and subtract word meanings. It's mind-bending, but it's statistical association, not human-like understanding. It just mimics it really well.
Okay, so words become numbers with meaning baked in. How do systems then make sense of them in order? In a sentence, a paragraph, how do they predict what comes next?
That's where recurrent neural networks, RNNs, come into play. Unlike simpler networks that look at inputs one by one independently, RNNs are specifically designed for sequences, where the order of the words is crucial,
Okay.
which is perfect for text and speech, right?
Yeah.
Sentences are sequences of words, punctuation, characters. Before RNNs, a machine reading a sentence might forget the beginning by the time it reached the end.
Yeah, that sounds like a problem for understanding context.
Yeah,
So how do RNNs manage to hold on to information from earlier, especially in long sentences? Do they have a kind of memory?
they do. That was the big breakthrough. They have these things called gated units. You might hear terms like LSTMs or GRUs. Those are types of RNNs with these gates. Think of them like smart filters inside the network.
Filters.
Yeah, they selectively decide which information from earlier words is important to remember and pass along, and what's irrelevant and can be forgotten. It acts like a selective memory. Really critical for things like sentiment analysis. The network reads word by word, constantly updating its guess about the sentiment based on what it's remembered so far. Capturing those long-range dependencies was huge.
So, okay, whether it's translation or generating a response, it boils down to predicting the next most probable word based on the context it's remembered and the massive data set it learned from. And this is where deep learning fits in. Lots of layers.
Yes, precisely. Deep learning just means neural networks with many layers, sometimes hundreds deep. These layers allow the network to learn incredibly complex nonlinear patterns, mapping inputs to outputs. For something like machine translation, they often use what's called an encoder-decoder architecture.
Encoder-decoder.
Yeah, sort of two-step process. An encoder reads the whole input sentence, say in English, and squishes it down into a meaningful numerical summary. Then a decoder takes that summary and generates the output sentence, maybe in French. It's been a massive step forward. Some systems even claim human parity on specific language pairs now.
Which brings us right to generating answers. When you ask something to ChatGPT, how does it actually put together a response that sounds so coherent, even creative sometimes?
Well, at its heart, it's a prediction game. It relies heavily on supervised learning, using those massive data sets we talked about. Supervised learning just means the AI learns from tons of examples where humans have already provided the right answer or label.
Okay.
You're basically showing it millions of examples of X leads to Y, and the system figures out the underlying pattern or mapping. So for these big language models, they've seen enormous amounts of text, where humans wrote questions and answers or summarized articles or translated between languages. The goal is always to learn a general predictor, how to classify things or generate a likely response.
That sounds a bit like IBM's Watson playing Jeopardy years ago. That was basically a question-answering system, right? Trained on old clues.
Watson's a great example, actually. An AI trained specifically to handle complex questions in, natural colloquial language. Its performance was extraordinary for the time. And like today's models, it worked by recognizing patterns. Given enough examples, it learns to spot statistical regularities and predict the likely answer or response. It wasn't understanding the clue like a human, but matching patterns. We even see similar ideas in reinforcement learning. That's where an AI learns by trying things out in an environment, like a game, and getting rewards or penalties.
Like AlphaGo.
Exactly like AlphaGo, learning to play Go. It played against itself millions, billions of times. It's called self-play. Basically learning a guess from a better guess over and over to improve.
So, pulling this all together, how would you characterize what these systems are really doing? Is it fair to say they're incredibly sophisticated pattern matchers, prediction engines, drawing on all that data but not actually thinking?
I think that's a really crucial distinction to make. It's easy to get wowed by the complexity, the performance. But yes, at the end of the day, they are building unbelievably detailed maps of statistical patterns in language data. They're marvels of statistics and engineering, always predicting the most probable next step based on those learned patterns. Not reasoning, not consciousness. They don't have aha moments.
Right, and this is where it gets really interesting, moving beyond the hype. Because they are impressive, but what are they not doing? Where do they fall short?
This is such an important point. While they absolutely excel at specific, narrow tasks, recognizing objects, playing Go, translating text, these deep learning systems often lack genuine understanding or common sense. Researchers like Oren Etzioni, Gary Marcus, they stress this. Deep learning is powerful, yes, a great tool in the toolbox.
But it's not the whole story for creating general AI. They're fundamentally advanced statistical models.
So, what kind of things trip them up? Well, simple common sense stuff. Ask the system, if I move my plant closer to the window, will its leaves grow faster, slower, or stay the same? Humans get that instantly. Light, photosynthesis, growth. The AI, it often doesn't have that background knowledge, that causal reasoning. It just knows statistical correlations it saw in text. It doesn't understand the world.
So it sees patterns but doesn't grasp the why, the purpose. It can't really simulate things or think counterfactually like we do.
Precisely. And another huge limitation is the sheer amount of data they need, specifically human-labeled data. Top researchers like Andrew Ng, Yoshua Bengio, they've pointed this out. Requiring so much labeled data is a major bottleneck. Supervised learning alone probably isn't how we get to general AI. We just can't label everything. Humans learn with way less data.
Right.
And this data dependency leads to what's called brittleness. They can seem miraculous in situations they were trained on, but then fail unexpectedly, sometimes catastrophically, in long-tail situations, slight variations they haven't seen before.
Like the self-driving car example. Handles normal traffic, but a weird obstacle stumps it.
Exactly. Or image recognition. They can be fooled by adversarial examples. Tiny, almost invisible changes to an image that make the AI confidently misclassify it. Think changing a stop sign slightly, so the AI sees a speed limit sign.
Wow, that's, unsettled.
It really highlights that their seeing or understanding is fundamentally different, much more fragile than ours.
So even when they hit superhuman levels on narrow tasks, they might lack basic abstraction. Or the ability to transfer learning from one area to a totally new one, which humans do all the time.
Exactly that. People like Bengio and Jan LeCun argue that human babies start with much more built-in structure, more sophisticated learning tools than we used to think. The idea that common sense will just magically emerge if you feed machines enough data, that seems pretty well overhyped. Deep learning makes tech smarter, for sure. But things like emotional intelligence, real collaboration, adapting intuitively with humans, they often lack that. They don't have a sense of self or their own goals. They're built to optimize our goals. Hashtag tag outro.
Okay, so what's the bottom line for you listening? This deep dive shows that systems like ChatGPT are incredibly powerful statistical engines. They're built on complex neural networks, trained on truly vast data sets. They are amazing at recognizing patterns, making predictions, generating text that really mimics human chat. And they've genuinely transformed things like translation and image recognition.
But, and this is the crucial takeaway, intelligence in these machines is very different from human intelligence. They run on probability, on learned associations from data. There's no real understanding, no common sense, no consciousness or self-awareness there. They are tools, incredibly useful tools, yes, but still tools. They'll
Obviously.
increasingly be extensions of our own capabilities.
So yeah, we've seen the impressive engineering, the huge impact, but also the very real hurdles still ahead if the goal is replicating nuanced, adaptable, truly understanding human intelligence. And maybe here's something to reflect on. If our most advanced AI, trained on more data than any human could ever see, still struggles with basic common sense, with genuine understanding, what does that really tell us about the sheer depth and complexity of our own intelligence, our amazing ability to learn so much from so little, and to always ask, why?